Welcome back, everyone. So yesterday we started our chapter on basically geometry, and we talked about triangles, all the different classifications of triangles, and the fact that the angles of the triangle, excuse me, have to add up to 180 degrees. Today we're going to broaden that a little bit. Instead of focusing on just the three-sided shapes, we're going to be looking at shapes in general and some of their properties. So a polygon, that's our fancy word for a shape, specifically a 2D shape. So any two-dimensional shape that's made up of three or more segments that connect only at their endpoints is technically a polygon. Now, many of the shapes that we're familiar with, triangles, rectangles, squares, hexagons, pentagons, those types of things, those are all polygons. But there is one common shape that we deal with that isn't a polygon because it isn't connected with segments, and that's a circle. So we can typically just equate the word polygon with shape, but we have to be careful. It does have to be a connection of segments to create that shape. So a circle, not considered a polygon because it's curved and there are no segments to create it. Okay? Now, just like the triangle had classifications, our polygons, all polygons, can be classified by the number of sides that it is made up of. And then just like the triangles, where all the angles inside the triangle had to make 180, all polygons have a fixed sum for their interior angles. It will just change depending on what shape we're looking at or what polygon we're looking at or how many sides it has. So yesterday our focus was on triangles, right? If we have three sides, we call that polygon a triangle. So this is technically the name of the polygon. And then we said that the sum of the interior angles was going to be 180 degrees. Okay, so hopefully we're good with that. Now, what about a four-sided figure? What do we call a four-sided figure? So some of you might be thinking a square or a rectangle. No, those are types of four-sided figures, but those are specific types of four-sided figures. In general, anything with four sides, any polygon with four sides, is called a quadrilateral. So that's the generic name for anything with four sides. Now, what do the angles add up to in a quadrilateral? So any four-sided figure, now just because we're comfortable with them, I want to think about a square or a rectangle. What do the angles in there have to add up to? Well, think about what it's made up of. If I was to cut this thing in half, I have two triangles. So if this triangle has 180 degrees total, and this triangle has to have 180 degrees total, then this has to have 280 degrees involved, which means there are, oops, let's put the degrees in there, which means there are 360 degrees total in the quadrilateral. And that's going to be true for all quadrilaterals, squares, rectangles, some of the others we'll talk about shortly. Okay? What if our polygon has five sides? A five-sided polygon is going to be called a pentagon. And what are the angles going to add up to in a pentagon? Well, think about what a pentagon looks like. Almost sort of like a house, right? So here's a pentagon. Well, if I cut this up, I could make this a triangle on the top, and then I can cut this four-sided figure here into two more triangles, which means I have 180, 180, and then another 180. Well, that's three 180s, three triangles, which means we have 540 degrees total. Okay? How about a six-sided figure? Six-sided figure is called a hexagon. Okay, a hexagon. Maybe you're seeing a pattern with some of the interior angles here. What's a hexagon going to look like? So a hexagon is going to be something like, this is really rudimentary drawing here, but something like this, where I could cut it into two quadrilaterals, right? Two four-sided figures. And then I could cut this quadrilateral in two, and I could cut this quadrilateral in two, and what do I have? Four triangles. That's 180 degrees, 180 degrees, 180 degrees, 180 degrees, right? So four triangles, 4 times 180 degrees. What is 4 times 180? Oof, don't mind my ridiculous math in here. 4 times 180 is 720 degrees. Okay, how about the next one? Next one we have a seven-sided figure. Now this is not one that we encounter a lot, so maybe you aren't familiar with the name, but we call a seven-sided polygon a heptagon. Now, I don't know exactly how I would even draw a heptagon. Any polygon that with 7 sides would make it work, but do we know what the sum of the interior angle is going to look like? Maybe you see the pattern. Triangle was 180 degree triangle, right? Then I had 2 of them, then 3 of them, then 4 of them, so the heptagon is going to be made of 5 of those triangles. And so if I had another 180 degrees here, we're looking at 900 degrees. Okay, 8-sided figure is called an octagon. Octagon's going to have another triangle added to it, right? Another 180 degrees, so 1080 degrees total. 9-sided figure is called a nonagon. It's going to add on another 180 degrees. And if I add 180 degrees to that, 1160 degrees total. 10-sided polygon is called a decagon. And that would add another triangle, another 180 degrees. So that would be, oh gosh, my mental math. It's going to be 8 times 180, so 1440 degrees. Okay, 11-sided figure is called an undecagon. And that would be another triangle added to the figure. Oops. Another triangle, another 180 degrees. So 1440 plus another 180, 1620 degrees total. 12-sided figure is called a dodecagon. That would be another 180 degrees. So 1800 altogether. And then after the dodecagon, after the 12-sided polygon, we have very non-specific names. So we would call a 13-sided polygon just a 13gon, and a 14-sided polygon would be a 14gon, and a 15 would be a 15gon, 16gon, so on. That's just going to continue. So anything after 14 is just the number. N could be any number, right? Followed by the gon, so an n-gon. Okay, now if it was a 13gon, we'd have 13 triangles. And then here we'd have 14 triangles. And so this would be 1980 degrees. And then 14 times 180. Oops, 180 is 2520 degrees. And then the last one. So there's a formula that's happening here, and I'm sure we can all see the pattern, but how do we take this and make a formula? No matter what number of sides we're looking at, I goofed here. Guys, nobody's yelling at me. This should be 11, and this should be 12. So let's just make sure I didn't screw up. I know I screwed this up. So sorry. 11 times 180. I think I had that right. I just, for some reason, I wrote the wrong number. 1980, that's correct. And then we need 12 times 180. 12 times 180, 2160. Not what I put there. 2160 degrees. I'm not sure how I jumped from 10 to 13. Okay, so anyway, we need a formula for this. So what if we were dealing with, let's say, a 20-sided figure? What are the sum of the interior angles going to be? Well, what we need is something for the n here. Now, if we have 14 sides, we multiplied by 180 by 12. 13 sides was multiplied 180 by 11. 12 sides multiplied by 10. 11 sides multiplied by 9. So every time here, we're multiplying 180 by what? By what precisely? Well, it's the number of sides, right? Minus 2. 14 minus 2 is 12. 13 minus 2 is 11. 12 minus 2 is 10. 11 minus 2 is 9. So the number of sides, n, minus 2. That's going to give us the sum for the interior angles for any polygon. Okay, now we have this nice little list, but if you have anything that goes beyond that, like a 20-sided polygon, you'd put a 20 in there, which would tell you to multiply 18 times 180, and you'd figure out your sum. Okay? So every polygon can be classified by how many sides it has, and just like the triangle, every polygon has a set or a fixed sum for the interior angles. All right? Now, if the polygon has all equal sides and angles, meaning it's equal angular and equilateral, we call it a regular polygon. A regular polygon. Okay, so we saw regular triangles yesterday. Regular triangle has 3 equal sides and 3 equal angles. We just called it an equilateral triangle. Can't spell all of a sudden. We called it an equilateral triangle. And because all those angles were equal, remember we said each of these angles was 60 degrees. 60-degree angles. Okay, so that's technically a regular triangle. All the sides are equal, all the angles are equal. We can call it an equilateral triangle, we can call it an equiangular triangle, we can call it an equilateral and equiangular triangle, or we can just call it a regular triangle. So those are all interchangeable names there. Now, what about a regular quadrilateral? If we had a 4-sided figure where all the sides were equal and all the angles were equal, first of all, what would all the angles have to be? So remember here, there was 180 degrees total. If we divided that into 3 equal angles, that's why each of those had to be 60 degrees. So if we take 360 degrees total in a quadrilateral and divide by 4 equal angles, then each of those has to be 90 degrees. So if we have a quadrilateral with 4 equal sides and 4 90-degree angles, then we can also call this regular quadrilateral a square. Okay, so a square is another name for a regular quadrilateral. Now, a regular pentagon doesn't have another name, it's just a regular pentagon, but it means, like the others, that all 5 of these sides are equal and that all 5 of these angles are going to be equal. Now, what are they going to measure here? Well, in the pentagon, we said there were 540 degrees total. If we take the 540 degrees total and divide it into 5 equal angles, that means each angle has to be 108 degrees. So each of these angles is 108 degrees. Okay? And then we have the regular hexagon. Again, this doesn't have another name. It just means that all of these sides are equal, and it means that all of these angles are equal. Now, how much would each of these angles measure? Well, the hexagon we said was 720 degrees total. So if we take the 720 degrees and divide it into 6 equal angles, that means we have 120 degrees for each of those angles. So each of those is 120 degrees. Now we can have any regular pentagon. I just wanted to show you a few examples. So all the angles are equal, all the sides are equal. We could divide the sum by how many angles or sides there are to figure out how much each one would have to be. Okay? So we have the gist of the polygons here, regular polygons, and then we have this family of quadrilaterals that we should be familiar with. So we mentioned earlier some specific names for our quadrilaterals. There are many quadrilaterals that can be classified more accurately based on their properties. I was trying to figure out what I wanted in the blank. Based on their properties, so basically what's going on with the angles, what's going on with the side relationships. So I have a little picture for you to sort of lay this out. So the quadrilateral just means that it has 4 sides. So any 4-sided figure can be called a quadrilateral. Now, if that quadrilateral has the characteristics of opposite sides being equal, so these are equal, and these are equal, not necessarily equal to each other, but the sides that are across from each other are equal, and they're parallel. Parallel we mark like this, so these lines are parallel, and then these lines are parallel. Then we have a parallelogram. So if we have 2 pairs of opposite sides that are congruent and parallel, we have a parallelogram. Okay, so that's that. Now, if we take the parallelogram and we head this direction, it still looks like a parallelogram, right? The opposite sides are parallel, and in this one, what's happening is not only are the opposite sides parallel, so these are parallel, but we also have all 4 of these sides being congruent. And if all 4 of the sides are equal, not just the opposite sides being equal, then we have what we call a rhombus. That one sort of looks like a diamond. Okay, the rectangle. The rectangle is like the parallelogram, right? We have opposite sides that are parallel here. We have opposite sides that are parallel here. Opposite sides congruent. opposite sides congruent. But to distinguish between the parallelogram and the rectangle is going to have 90-degree angles. Now if we put together the 90-degree angles and the fact that the opposite sides are congruent and parallel, then we have the square. So in the square, all sides are equal, all angles are 90 degrees, and we know opposite sides are parallel. Okay, now we have a few other oddballs here. We have the four-sided figure called the kite. Get rid of this. We have the four-sided figure called the kite. Nothing's going to be parallel in a kite. What will happen is you have two pairs of sides that are congruent, but they're adjacent sides. That means they're next to each other. So these two sides are equal, and these two sides are equal. And then also these angles in between those non-congruent sides are going to be equal. Okay. Four-sided figure that has only one pair of parallel sides is called the trapezoid. So we have a pair of parallel sides here. And that's all we need for a trapezoid, so nothing has to be true about the sides, the side lengths or the angle measurements. Now if we have what we call an isosceles trapezoid, it's just like the isosceles triangle. That means not only do we have a pair of parallel sides, just one pair, but we also have these sides in between them are congruent. Two congruent sides, two equal sides. That's what an isosceles triangle is, and that's what an isosceles trapezoid is. Okay? So it's not that you have to memorize all the properties. I just wanted to make sure that you're familiar with all of those names. And that's really true for what we talked about here. You don't necessarily have to have all these memorized, especially since you have access to your notes, but I just wanted to put these names on your radar. Okay? Okay, so now what I want to walk you through is some of the problems that you might encounter based on the information that we've talked about. So you should be able to, like with the triangles, figure out missing angles in any polygon. So the first thing we want to do is classify our polygon. Let's decide what it is so that we know the sum, okay? And we can either refer to the list that we created, or we can use the formula that says take 180 and multiply by n minus 2. All right, so look at number 1. Before we try to find the measure of the missing angle, what kind of shape are we dealing with? Well, we got 1, 2, 3, 4, 5 sides here. So if we have 5 sides, then we have a pentagon. And a pentagon, the sum of the interior angles for a pentagon is 540 degrees. So we're trying to find this missing angle right here, angle 1. I know if I add the 95, the 140, 95, 140, 100, 114, and the missing angle, I have to get to 540 degrees total. So we're going to add all this up. 95 plus 140 plus 100 plus 114 is 449. So 449 degrees are in there total. If I subtract that from 540, I'll get that missing angle. So 540 minus the 449 is 91. So we have angle 1 is 91 degrees. Okay, so then we're going to look at number 2. Same, oh my goodness. Number 2, same kind of thing going on here. So we're trying to find the missing angle, but notice angle 1, this missing angle over here is outside of our shape. Now what kind of shape is this? 1, 2, 3, 4, 5 sides again. So again, we're dealing with a pentagon. So we know the sum is 540. So let's see. I know the sum is 540, but the only way I can use that is if I knew 4 of the angles, then I could figure out, let's say, that missing angle. So I can't start with that sum. But this is going to tie into something we talked about yesterday. Remember, a straight angle, a straight line measures 180 degrees. So if this angle is 48, if I subtract from 180, I'll get the missing angle here. So 180 minus 48 means that missing angle is 132 degrees. So here I have 132 degrees. So 180 minus 48 got me that guy there. All right, then we can do the same thing here. This is another straight angle, another 180 degrees. So 180 minus 104 will tell me that other angle. All right, so if I have 180 and I take away 104, that's going to leave me 76. So 76 degree angle here. And now we have 4, why did I erase that? This was 180 minus 104. Now I have 4 of the 5 angles inside the pentagon, so I'm going to start by finding this. Let me call it X, so I don't have too many question marks here. If I add 99, 132, 115, and 76, and X, if I add all 5 of those angles, I have to get 540 degrees total. So let's go here. 99 plus 132 plus 115 plus 76 is 422 degrees. So 422 plus X has to equal 540. If I subtract that over, 540 minus the 422 is 118. So 118. So this angle here is now 118 degrees. And now we can use our straight angle again. These two have to make 180. So to find angle 1, just get rid of that. To find angle 1, we're going to take 180 and subtract the 118. And 180 minus 118 is 62. So 62. Angle 1 is 62 degrees. Okay, not so bad. It's a lot of adding and subtracting, but we have calculators, so not horrible. Okay, now it's number 3. Feel free to pause and give this a shot. Otherwise, let's classify here. What do we have? 1, 2, 3, 4, 5, 6 sides. So this has 6 sides. Then we have a hexagon. And the sum for the angles inside the hexagon is 720 degrees. So the 106, the 153, the 114, the 135, the 144, and 1, 2, 3, 4, 5. The last missing angle here has to make 720 altogether. So let's add up what we have. Let's see, 106 plus 153 plus 114 and 135 and 144, 652. So we have 652 plus our missing angle equal to 720, so I just have to subtract that over. 720 minus the 652 makes that 68 degrees. So angle 1 is 68 degrees. Okay, just for some uniformity here. Alright, so last one, again, feel free to pause the video and give it a shot. We're looking for the measure of angle 1, which is outside of the regular hexagon. Now, we looked at the regular hexagon in the front. We said the hexagon has 720 degrees total, and if we divided that into 6 equal angles, we said each of those angles would have to be 120 degrees, right? Just make sure. I guess I should have checked this earlier. 720 divided by 6, yeah, 120 degrees for each angle. So all these angles, particularly this one here is what we want to focus on, are 120 degrees. And again, this makes 180 total, makes a straight line, a straight angle. So all we have to do is subtract from 180. So angle 1, oops, let's get off the highlighter. Angle 1 here has to be 180 minus the 120, which makes it 60. So angle 1 is 60 degrees. Okay, so hopefully you're feeling like those are pretty manageable. What I want to show you next, lastly, is the other sort of random part to this section in the book, and that's perimeter. So whatever your polygon is, you should be able to calculate its perimeter. If you're not aware, the perimeter of a polygon is the total distance around the outside of the polygon. So the distance around the outside, if you were to walk along the outside of a rectangle or walk along the outside of the triangle, how far would you have walked type of thing. So to find the perimeter for a polygon, you're simply going to add the side lengths. So that's pretty straightforward. Now, circles, remember, are not polygons, but you should still be able to find the perimeter. Since it isn't a polygon and you can't add the sides, you are going to use a formula. Now, the perimeter for a circle has a special name because it's not a polygon. We call it circumference. The circumference of a circle, that's the same thing as the perimeter, and there are two ways to calculate it depending on if you're given the radius of the circle or the diameter of the circle. So circumference, which we're going to call c, can either be found by multiplying pi times the diameter, or it can be found by multiplying 2 times pi times the radius. So just so we're clear, c is circumference, d is diameter, that's all the way across the circle and through the center, and then r is the radius, that's half, that's from the midpoint to the end of the circle. So if you want to use that formula, make sure you're keeping those variables straight, okay? And then pi is approximately 3.14. Pi is approximately 3.14. All right, so number 5, if we wanted to find the perimeter for this shape here, it tells us it's a rectangle. Now obviously by looking at it we could see it's a rectangle, but we don't want to assume any properties. But since it's a rectangle, that means that this side is also 12 centimeters because opposite sides are congruent, and this side is also 6 centimeters. So this perimeter is just going to be 12 plus 12 plus 6 plus 6, which is going to be 12 and 12 and 12, 36, and that's centimeters altogether. So if you were to walk all the way around there, trace all the way around there, you'd be tracing a total of 36 centimeters. So the perimeter is 36. Okay, now 6. If we want to add up all the side lengths, we have to know all of those side lengths, but we have one missing. Do you remember from yesterday how we're going to find this missing side length? So remember, this is a right triangle. It's got the right angle in it, and right triangle, we can find a missing side using Pythagorean theorem. So let's say this side is A and this side is B. Then A squared plus B squared would have to equal C squared. So 5 squared plus 12 squared is going to have to equal C squared. So this is 25 and 144. If you add those, you get 169. So what is the square root of 169? C is going to equal, I know this, but I just want to make sure you know how to use your calculator. The square root of 169 is 13. So C equals 13. Now, that wasn't the goal of this problem. The goal was to find the perimeter, but now we can do that. So the perimeter says add up all the sides. So we've got a 12, a 5, a 12, and now the third side is, we said, 13 inches. So our perimeter is going to be 5 plus 12 plus 13. And that's 17 plus 13, which is 30. So 30 inches for that perimeter. Okay, moving right along. So we have a pentagon here and a regular pentagon. Regular means all of the sides are equal. So all of these sides are all going to be 6 meters. So if we have 6 meters, 5 times, right? 5 times 6, or you can write that out. 5 times 6 would be the quick way to do that. Otherwise, 6 plus 6 plus 6 plus 6 plus 6, 5 times. Either way, you're going to get a total of 30 meters. Got a lot of answers in 30s. That's just coincidental. Okay. Now our last one's not a polygon. So a circle, when we find its perimeter, we call it circumference, and we're going to use a formula. Now in this case, we're given the radius is 3. If it went all the way across, we would call it diameter and use the diameter formula, but it's the radius here. So a radius of 3. Circumference says that, or to find the circumference, we're going to multiply 2 times pi times radius. In this case, 2 times pi times our radius is 3. So we can say that 3 times the 2 would make 6. We could call this 6 pi, and that would be feet. And this would be the exact answer. And that exact answer is, we would say it's in terms of pi. If you were asked to approximate that, then we could also say C is approximately 6 times pi is 3.14. So we would say it's approximately 6 times 3.14 is about 18.84. 18.84, and again, that's going to be feet. So I'm not sure when you're working on Math Lab which one it's going to prefer. I prefer the exact answer, but if you're asked to approximate, then you're actually going to multiply out the pi. So for the exact answer, you're going to leave pi, and then this one is the approximate answer. And for the approximate answer, we multiply by pi, multiply by 3.14. Okay, so the exact answer leaves pi in there. The approximate answer, you get the decimal by multiplying by the 3.14. All right, that is it for today. Hopefully it's not too much. I know it's 3 pages of notes. I'm sorry if you're printing. Did my best to cram as much as I could on 2 pages. Anyway, if you run into any questions or struggles along the way, please feel